Hello, everybody. My name is Christopher Mick, and I run the STEAM educational nonprofit Space St. Croix. And that's based here in Hudson, Wisconsin. And I do a lot of school-based programs, both public and private, and homeschool programs for everyone in the Hudson, Wisconsin School District. Also do programs at the Hudson Area Library. And going to talk today about hydroponics in space with you. So I'm sorry I can't be there in person. But these videos were kind of being produced to help get programs out to schools that would be normally doing in person. So today's topic is hydroponics, and this one is kind of near and dear to me. So also wanted to give a shout out. It's Women's History Month, and activities going on all month with other programs we're doing for other schools, but wanted to show a quick slide. Some of you are familiar with Katherine Johnson from Hidden Figures. If you were able to see that movie a few years back, and going through the long career of females working at NASA all the way to the current astronaut class, which is about a 50% rate now. So there's 6 men and 6 women in the astronaut class, and a lot of amazing scientists and researchers working at NASA. And we'll be doing a lot of other programs focused on that this month. So just want to give a shout out for Women's History Month. And then today, getting into our main topic here. So sorry, just checking if I have all my slides set up here in proper order. So hydroponics, depending on what you've already learned, going to just do a quick review here. And actually on a personal connection, my father designed and built hydroponic greenhouses in the late 70s and sold them to different companies for unique designs for their particular needs, and actually had a 10,000 square foot greenhouse when I was about, I think, 10, 11, 12 years old in that area in Northern California. And we grew hydroponic cucumbers and sold them to local grocery stores. So I could talk to you about this subject on the engineering and on how NASA is looking to this work, but that also can interject with you a little bit of a personal angle as well. So really quickly, this might be a hydroponic situation you're familiar with if you ever saw one on a school field trip. Or have visited one of these facilities. They could be designed many different ways. This is a pretty straightforward design. If you can see my cursor around here, I'll just be pointing out a few things. So the hydroponic crops in standard rows, scaffolding to allow the vines to continue to grow up and have something to grab onto. And then you'll notice a few engineering things here. There's a misting system in the pipe lattice work around the structure, which will kind of create almost a steam to control the warm temperature inside the greenhouse. So it's usually on a timer system, and a misting apparatus will kick in on a regular predictable cycle, might be once every 15 minutes. It'll increase the humidity inside the greenhouse. And then there's also light fixtures here. So the greenhouse has the option to not only utilize the power of the sun during the day, but you can also have grow lights kick on in the evening hours. So you have growth happening 24/7. So we'll talk about the differences in growth rates for hydroponics over conventional farming, but just kind of wanted to give you a general layout of the structure. And then you kind of see an early stage of seed beds here, and then they get transferred and rotated out through the regular rows once they've started to sprout. There's also fans periodically around, again, to help kind of control the climate, to push that humid air around, or to lower the temperature if it exceeds. There's sensors all around the greenhouse for measuring moisture and temperature and humidity, and those are all in place to kind of regulate that and keep it at a consistent optimal growth level. So again, some of the basics. Hydroponics is a way to grow plants by use of a nutrient-rich water solution. So we'll take a greater look at that in the next slide. But that is the main difference between hydroponic and conventional farming, where hydroponics, you're providing all the nutrients in the water solution directly to the roots. No soil is required, as with conventional farming. Skipping down a little bit, you just need a media to grow whatever plant you're growing, tomato plants or cucumbers or others. What have been used, we used on our farm, was sawdust, bags of sawdust that was left over from a local construction company. was a very readily available, very cheap product, and we would buy bags of the sawdust and use that as the growth medium. It just gave enough for the roots to kind of grab onto to provide a foundation for the plant. But you'll see netting used, sand, rock, wool, clay, pellets, other things used on that. The growth rate, one of the advantages for hydroponics, you grow at a 30% faster rate than traditional farming. So if, again, sticking with the examples mentioned before, if you're growing tomatoes or cucumbers, you're getting those to fruit and to bear and to be able to pick 30% faster than if you did the same planting at the same time on a conventional farm. No soil required. Again, jumping back, just whatever media you're using. And that helps a lot with the farming and some of the things that come up conventionally with pesticides not needing to be used in that. Per the previous slide, the humidity, the lighting, and the temperature are controlled to optimize the growth. So it's kept warm in the greenhouses. You're maximizing the lighting, as you can see with the structure, where it's either a plastic or a fiberglass construction to allow all the light in. And then you can even structure additional lighting to be having a light on the plants 24 hours a day. And then the humidity and the temperature are kept in kind of a warm. If any of you have visited like a botanical garden, you may remember that, where it's kind of warm in that area, which kind of promotes the growth. The structure maximizes the light to the greatest effect. No need for the use of pesticides for pathogens found in conventional farming. So chemicals like Roundup and other things like that, where you need to keep the weeds and different bugs away that might be attacking your crops, that is not present in a greenhouse because you're not using soil. So there are no pathogens that will show up in the soil, and you have a closed environment. So as long as you're not letting any things into the greenhouse, they are not going to propagate in that environment. No limit on the footprint or design. And by that, we mean, I showed you a pretty conventional greenhouse in the previous slide, but in urban environments, they've gone vertical, they're stacked, they've been put in like train containers, rooftops, towers, all of that. So the greenhouse can be arranged in whatever way optimizes for the space that's available. And then looking at jumping ahead, we'll be looking at the next slide. 13 macro and micronutrients are added to the hydroponic water to kind of provide that nutrient delivery system for the plant. And here's a look at that. Let me get my picture out of the way here on that. So you can see the nutrients from the air and the nutrients from the water on a normal growth cycle for conventional farming. All of those compounds are put into the water solution and delivered directly to the roots. So on conventional farming, a lot of energy and mass and time is dedicated to the establishment of the root structure of whatever seed has been planted, to anchor it, to go hunt for those nutrients in the soil. And so the roots get thicker, they grow longer, they're searching out for these items. Because you're delivering in hydroponics all of this nutrients right to the root system, they don't need to spend time on searching for it. And so that time and energy is redirected toward the production of the fruit that you're growing, not on the structure and on the searching for those nutrients. So I mentioned a little bit about vertical structures. I just wanted to throw one slide. This is a rack system where they grow hydroponics vertically. And so these are done as many as can fit in the space in these single kind of wall units and take advantage of availability of a vertical space, but maybe not so much horizontal space in an urban area where you're doing that. So this is just one section pulled out to kind of show you how it operates and how many plants you can fit in that vertical section. And then the photo on the left here is of a pillow, which is the main component of how plants are grown on the International Space Station right now. The ISS is kind of the test bed for growing plants in a microgravity environment and trying to optimize that process for not only space station crews, but looking ahead towards long duration space missions, setting up a base on the moon, setting up a base on Mars in the future where you're going to have long-term occupants, and they are going to be looking to produce their own food instead of having it all delivered by resupply vehicles. So just wanted to point out a couple things on these pillow arrangements. You'll see the kind of elastic cords to hold the pillow down because we're in microgravity. This photo was taken up on the International Space Station. And you have this pillow that has a kind of netting material in it to provide that foundation for the root to take hold when the seed germinates. And then you have this area where the baby lettuces are coming through. And this is the syringe area where it's pre-inserted. So when water is hooked to this syringe, it'll be able to deliver it right to the root system. And we're measuring how much water each time is being put through the syringe because we're trying to optimize the system on what is the least amount of water that we can use, because water is a valuable commodity up on the International Space Station. And we'll talk about that more later, but this is just kind of the arrangement for how the pillows are sorted. And this is the International Space Station where all this work is taking place right now as we speak. About 250 miles up, orbiting at 17,500 miles an hour. There are 7 astronauts up on the ISS right now as we speak. And then this is the inside, a wider shot of one of these veggie is the name of the growth chambers that are produced by Sierra Nevada Corporation and are flown up to the International Space Station. And we grow different plants and vegetables and flowers, testing how well they do, changes that might need to be made to improve a crop, any problems that came up with a crop. So you saw like a micro greens for baby lettuces that are edible, zinnias, the flowers are pictured here. So every pack is labeled. You can see those syringes pre-inserted, these pillows with the cords holding them down. And then this is the container. It's an expandable kind of an accordion plastic that can raise or lower depending on the height of the plants as they're growing. And at the top of it that we're not seeing is the LED light source. It's the top of this chamber. And that kind of shows you that kind of reddish pink color. That's the optimal spectrum for plant growth. The LEDs are very low energy consumption lighting arrays. So that's another effort to try to minimize the energy that you're expending. And this is what one of the veggie chambers looks like, with some just being planted and not having germinated yet, and others kind of in a full growth or continuing to grow. And then another shout out continuing for Women's History Month. We have Jessica Meir here at the top, and then Christina Koch at the bottom with the glasses. Christina Koch recently set the record for the longest stay by a female astronaut in space. She just about a year she spent up on the International Space Station. And this is the photo of the 2 astronauts working at one of the veggie stations. So you saw that close-up photo earlier. This is it kind of widened out where you see them working on the ISS and maintaining the experiment and tending to it and checking the growth, pruning, checking the watering, monitoring if any lighting adjustments, measuring the growth, all of that on how things are going with the veggie experiment. And then this is astronaut Scott Kelly. He set the current record. He spent just a few days longer, a handful of days longer than Christina Koch did, but a year-long mission on the space station. So he's the current record holder for U.S. astronauts at about 340 days, I believe, was his total stay on his almost year-long mission on the space station. And he and Kai Lundgren, the other astronaut, are eating some of those microgreens that were shown in an earlier photo, these baby lettuces they were growing. And they're taste testing. They're figuring out how their crop tasted, if there's any feedback for the scientists and engineers that are developing the veggie containers for future feedback for different things to try to grow, texture, taste, smell, all of that on how it went. So they all reported they tasted very well. They were very excited to have them because, as you can imagine, the bulk of their diet is kind of prepackaged material, where it's equivalent of like a mac and cheese or like campfire food, where it's you have to inject some water into it, mush it all up in the bag, and then you're heating it to have your instant meal prep. So the fresh vegetables were a very welcome addition to the routine on the International Space Station. And this work is currently being done. So I just wanted to give, these are happening all the time, but this is one that we're right in the middle of Growing Beyond Earth Maker Challenge. So This is the second year of this project, and the goal for this project is autonomous plant systems. So there's 3 different groups that are competing in this: the high school, the college, and the professional category. And the design challenge for this one is to come up with a 30-day self-sustaining design where, as you can imagine with some of the previous photos I showed, we are growing food on the International Space Station, but it requires a lot of astronaut involvement and attention: the watering, the pruning, the checking, if the plants are declining and need some help and adjustment in their water or their light. And the astronauts spend quite a significant amount of time maintaining those veggie systems. And the goal is to try to find a system to get away from that, where it can be more run on its own by sensors and cameras, and that if there is an adjustment that needs to be made, the software can be taught how to take care of it, to adjust the water, to adjust the light, things like that. So the top 5 vote getters in each category are awarded cash prizes. And some of these top vote getters will actually be selected to have their version flown up to the International Space Station to kind of field test it to see if this is something that will work as intended. And again, there can be feedback provided by the astronauts and the computers on board the ISS to give feedback for refinements or changes for a future version. But this is all towards looking to improvements on this technology to be able to be used on more and more upcoming missions. And this is one of those concepts for an upcoming mission. This is a lunar base proposal. So you can see the astronaut here close to the screen, and then these series of domes where there's 3D printed structures using the lunar regolith to kind of make shielding for the structures, because radiation is a big concern when you get away from the radiation belts, the Van Allen radiation belts that protect the Earth. When you get away from that area, you're exposed to a lot more gamma, X-ray, ultraviolet radiation from the sun, which can be damaging, obviously, to humans, but can also be damaging to their living quarters and to any plants that you would be growing. So 3D printing with regolith, which is the lunar material, into structures that you want, can provide shielding and protection from that environment. And so if there were greenhouse stations in one of these domes, they would be protected by that regolith layer. And then this is what a concept for one, kind of a cutaway you're seeing on Mars. So this would be like a habitat chamber for the astronauts, where it might be their labs or bedding accommodations, exercise area, and then this would be a module for the food area. So they completely fill the container going along the walls. They're just doing a cutaway to show you where people would enter and exit in the size of the unit and would be growing their crops in a situation like that. Some of the goals for this, as we stated, are to test things on the International Space Station, to make refinements to it. We want to develop these technologies for deep space missions for astronauts that'll be returning to the moon, that'll be doing missions to Mars or an asteroid, that'll be longer term space durations. Moon and Mars, we looked at some of those base concepts for that. And one of the concepts to aid in the radiation exposure for humans in space is called a green wall, which is pictured here, and we'll see some photos of before. Water is a great barrier to radiation, kind of a shield to radiation. So one of the thoughts by a smart engineer was, what if you line the walls of whatever structure you're traveling in with these plants, where they have their water delivery system in the lower part of the chamber here, and those can be built into the walls. So not only are you growing plants, but you're also getting radiation shielding, kind of being enclosed in water with that in the walls of the vehicle. So this is a proposal for a future, Bigelow is the company that makes these inflatable space stations. And this is one of their concepts for a future space station, where it would have these green wall segments built into it. The astronauts would have their living accommodations in the center of the vehicle, and they'd like to measure the radiation levels experienced by the crew on the inside, and then again see if they need to optimize it, more water, less water, different design, and that. But that's a test concept that they would like to fly within the next 5-6 years they're looking at. And then this is Sierra Nevada Corporation. This is their green wall concept in practice. So these are two different versions of their green wall system. So I actually saw these at their facility in Madison, Wisconsin. This is being done, so in our state. But again, if you can imagine these wrapping all the way around, they're just showing you kind of a half section, but that'd be that circular structure where it'd be these individual plant beds with the LED lighting where they can control. And then the water systems are in the backs of these units, kind of facing the exterior wall to the spacecraft. And so these, you can see on the specs in the bottom, each unit's about 9 feet tall. The modules are 4 feet by 2 feet by 2 feet with the LED built-in lights. And then this is a mock-up of it being in the spacecraft form that Sierra Nevada Corporation had. This is at their facility in Colorado. One of their engineers kind of walking down the proposed area, you know, where the astronauts would be floating through, but kind of showing you the relation to Astronaut being inside it, that kind of green wall concept. So that's very interesting and could provide a lot of solutions for the problems of food production and kind of radiation protection. And then this is an interesting one. Again, when I was down in Madison, I took this photo when I took a tour. Back then, the company was called Orbitech, and they've since been acquired by Sierra Nevada Corporation. So now it's just Sierra Nevada Corporation. But if you see these Orbitech labels and photos I took, that's because that was the name of the company back then. But they've also experimented with in situ growth situations. And in situ means making use of what's there where you are. And so these are structures made from wheat. They would grow wheat, and they can form and cast these different molds just out of the wheat that's grown. And it can also be used to provide the media for future plants, whatever you're growing. When you grow a crop of wheat, you can dedicate some of the wheat to making these structures that can be in place of, again, soil, or like peat pods. Little peat pods are what are used on some of the experiments. And again, that just adds volume and weight that you'd have to pack. So if you just have your seed pillows, and then you know you can grow wheat in your first crop, you'll be able to make these kind of media structures that'll hold the roots of whatever you're growing later, you know, tomatoes, cucumbers, things like that, the lettuces in the future. So that's a really neat thing where, again, you can make structures that you can use just out of the crops that you're growing, and that can help you kind of self-perpetuate the resources you need for your crops. So we've talked about a few of these, but the benefits to human space missions, you reduce the cost and complexity and the mass of the ECLS system. NASA loves acronyms, so I had to slide one in there. ECLS is Environmental Control and Life Support Systems. So in every spacecraft that has astronauts on it, you have to have an ECLS system. So that is your climate control, the temperature, your breathing air, your filtering system for pulling the carbon dioxide out of the air, your system for recycling any unused oxygen and putting that back into the system. So if you can think of it like that. And if you have plants growing, as you can guess, you're getting oxygen produced. The plants are breathing in some of the carbon dioxide. Also filtering water that's going through them. So having plants on board would also offset how much and how big of an ECLS system you would need to build on your spacecraft or your base. So that would help in that area. It would also reduce the need, the weight, and the storage constraints of additional pre-prepared meals, as we talked about. If you're growing your own food in addition to the food that you have packed, the less of that you need to pack, because they're able to augment their calorie intake and their meals with things that they're growing at their base or on their mission. And the radiation shielding, we talked about the green walls concept, could help if there's a solar flare event while you're on your moon base or while you're on your way to Mars. And it would be a lethal dose of radiation due to a solar flare. The crew can be notified that the flare event is happening, and they can make sure they are habitating in the area that has the green walls in their ship and provide them necessary radiation shielding. Psychological benefits have also been shown for crew living with the crops. Eating fresh produce makes you happier that you're just not eating prepackaged meals all the time. The tending and the care for the plants, having something green and living with you, they're all a positive psychological factor. And then the potential to allow for what NASA calls a closed loop system. So right now, the International Space Station is the best thing we have, and that is a partially closed loop where we still need to resupply the spacecraft. They recycle a lot of water on the space station. They recycle their urine. Any wastewater from breakfast or meals is all turned and processed back into drinking water. The sweat, when they work out and exercise, that all gets grabbed and turned into drinking water as well. So they reclaim a lot of oxygen, they reclaim a lot of water, but they're still not at 100% for a closed loop system. So they keep improving it as we've gone along in the 20-year timeline of the International Space Station being occupied by crews, but we're not at 100% yet. And having green walls and plants growing would help to close that loop where they would provide all the things we just talked about. And then you also have things that are helping that process along. Their Mars Perseverance rover, you may have heard about in the news recently, just landed on Mars. It has an experiment on board called MOXIE, another acronym, but pretty much it's making oxygen from the atmosphere of Mars, which is primarily carbon dioxide. And so it is pulling an oxygen atom away from the other in carbon dioxide and attracting that to other oxygen atoms and making just a container of oxygen as it processes. So that would be huge to astronauts. For that example, doing a mission to Mars, you could send a large machine scaled up that would be doing what MOXIE's doing, and it would just be sitting there for however long you sent it, years in advance of a crewed mission. It would be making oxygen, which you can use for breathing when you get there, and you can also use it to turn into rocket fuel, because rocket fuel is usually liquid oxygen, liquid hydrogen. Some processes are also being discussed for making methane on Mars, because you can make a methane-powered rocket engine. So the resources are there on Mars to do a lot more in situ production and hopefully get to a point where we could achieve a closed loop system. And then a lot of these experiments we're talking about are done on ground-based, Earth-based systems as well. So they'll compare their Earth experiment to what's happening, for example, on the International Space Station at the same time. So this is an example. This one, you can see the LED lights at the top of the box. This is the same dimensions as one of the growth chambers, the veggie chambers on the International Space Station. This one's being used on Earth, and they are growing wheat, as we talked about before, and they are, again, trying to get the data and optimize things to be the best performance possible. And that ties into some of the goals they have. They want, as I said before, they want to find what's the minimal amount of water we can use and still generate healthy crops. What's the minimum amount of energy we can expend through temperature control and through the lighting to get a good yield? What is the best yield we can get out of any given seed? What are the best things to grow? They're going to determine on the space station. And then tying into that student competition, that 30-day autonomous goal they have for that competition, going for minimal attention. Can we get this where to the point it's a mature technology where it doesn't need so much day-to-day human intervention and maintenance for that? So those are my slides for that. And some of the experiments we do here in Hudson. So you may have heard about, this is one called Tomato Sphere. So these are identical packs of tomato seeds. You'll just notice one has a label with N typed on it and the other is P. And so nobody knows which until you finish your growth experiment and send in your results. But one of these two bags lived on the International Space Station for 6 months, was exposed to a microgravity environment and to the extra radiation dosage being 250 miles up at the space station. And the other pack of seeds was just off the shelf. And so students will grow both packs, track the growth rate, track how much water they were providing the plants, and then note any differences in the growth on the plants and try to ascertain if they can figure out which ones were the seeds that lived up in the International Space Station. So that's something I work with a lot of students in the Hudson area on that are participating in that. So that's a little overview of the hydroponics, the way NASA looks at it. Hydroponics are used a lot in earth farming, as we saw in the earlier photos all the time, and they're being looked at as a kind of optimal way to help crews in space, because those things we talked about, much more accelerated growth, needing much less resources, on hand, like heavy amounts of soil and things like that for producing the crops. And it's kind of an optimal way to that lends itself towards space exploration and helping out with those ecless environments. So I hope you learned a little bit about hydroponics. It was great to talk to you on that, and hopefully we'll see you again with another presentation soon. Thanks a lot.